Have you ever stopped and wondered how a machine really learns? I'm not talking about some sci-fi movie concept, but how it works in the real world every single day. Well, today, we're going to dig into the fundamental tools that actually make it all happen. When it comes down to it, it's all about these powerful algorithms called machine learning models. The best way to think about them is like different strategies or game plans that a computer uses to find patterns and make decisions. It's kind of like how you wouldn't use the same strategy to solve a crossword puzzle that you'd use to win a game of chess. So here's our plan for this explainer. We're going to build this up from the ground floor. We'll start with the simple idea of drawing the perfect line. Then we'll level up to something that's kind of like a game of 20 questions. From there, we'll see what happens when you harness the wisdom of the crowd, and we'll finish up by looking at how you actually go about building an artificial brain. Okay, let's dive right in with the most basic idea in all of classification, finding a boundary. If you've got two different piles of stuff, how do you separate them? The simplest answer? You just draw a straight line. Just imagine for a second that you plotted all of your emails on a big graph. You'd probably see the spam messages all clustered together over here and your important emails grouped together somewhere else. A linear model's job is really, really simple. Just draw a clean straight line right between them. Everything on one side gets labeled spam, and everything on the other side is not spam. That's it. But here's the thing. Not just any line is going to cut it. If you draw a line that gets way too close to the data points, you're taking a big risk. A new email could easily pop up on the wrong side of the line. So the best line, the smartest line, is the one that gives both sides the most possible breathing room. You want to create the widest possible street right down the middle. And this idea, maximizing that street, it actually has a technical name. It's called the geometric margin. The classic algorithm that was built to do this exact thing is called a support vector machine, or an SVM. By finding that line with the biggest possible margin, the SVM creates this high-confidence boundary that's just way better at classifying new things it's never seen before. Okay, so drawing one perfect line is a great strategy for sure. But what happens if your data is messy and you can't just slice it in two with a single straight line? Well, this brings us to a completely different approach, one that forgets about drawing one line and instead starts asking a series of really simple questions. And that is the absolute essence of a decision tree. It carves up all the data by asking a sequence of simple yes or no questions. So yeah, think of it less like trying to find one big grand divider and more like you're building a flowchart of decisions that's going to lead you to the right answer. Let's see how this actually works. Say you want to predict if you can go skiing. A decision tree might start by asking, okay, is the latitude greater than 30 degrees? If the answer is yes, it focuses just on that group and then asks another question, like, all right, is the month before April? You see what's happening? Each question splits the data into smaller, more specific little boxes until the tree gets to a point where it can make a really confident prediction. A single decision tree is pretty clever, but it definitely has a weakness. It can get way too specific, and then it totally fails when it sees new data. So what if we can move beyond just a single tree and harness the power of an entire forest? Right. The problem with a single, deep decision tree is something called high variance. And what that really means is that it can learn the training data so perfectly, it memorizes every little quirk, that it gets completely tripped up by new data that's just slightly different. It's exactly like memorizing the answers for a test instead of actually learning the concepts. The solution to this is a really powerful concept called ensemble learning. And the core idea? It's super simple. A group of diverse experts will almost always make a better decision than just a single one. And we can apply that exact same logic to our machine learning models. And a perfect example of this is the random forest. It builds a whole forest of decision trees, but with a really crucial twist. Each tree is slightly different. They're all trained on random little chunks of the data, and each tree is only allowed to consider a random subset of features when it asks its questions. This forces diversity, and it makes sure the trees don't all make the same mistakes. The final prediction? It's just a majority vote. It's basically democracy for data, and it is incredibly effective. So all of this builds up to the final model in our journey, and this is the powerhouse behind so much of modern AI. We're talking everything from image recognition to language translation. We're talking about the neural network. Now, the whole idea of an artificial brain can sound incredibly complex, right? But the secret is that it all starts with just one single, simple building block, the artificial neuron. And here's where our whole journey connects. A single neuron, well, it does something that should sound very familiar by now. It's basically a tiny little linear model, just like the one we started with. It takes in a bunch of inputs, it assigns an importance or a weight to each one, and then it makes a simple decision about whether or not to fire an output signal. One neuron by itself isn't all that powerful. The magic really starts when you connect a whole bunch of them together into a layer. Now you have a whole group of these tiny decision makers, all looking at the same input data at the same time, and each one is searching for a different, simple pattern. But the real magic, the reason we call it deep learning, is what happens when you stack these layers. See, the output from one layer doesn't become the final answer. Instead, it becomes the input for the next layer, which then feeds the next and the next, creating this incredible cascade of computation. This layered structure creates a hierarchy of features. So to recognize a cat, for example, the first layer might learn to see really simple things, like edges and curves. The next layer up combines those edges to find more complex shapes, like ears and whiskers. And then, by the time you get to the final layer, the network is combining those features to identify the super abstract concept of a cat. So, we've gone on this whole journey, right? From drawing a single line with an SVM, to asking questions with a decision tree, to consulting a crowd with a random forest, and finally, building an artificial brain with a neural network. Each step just represents a more and more sophisticated strategy for finding patterns in the world. And this whole progression from simple lines to these incredibly complex networks, it's far from over. As researchers develop even more powerful models, it just leaves us with this one fascinating question. What are the hidden patterns in science, in art, in our own society that they're about to reveal to us next?